Hi everyone, welcome back. In this lecture we're going to look at the kinds of information that the first derivative and the second derivative tell us about the graph. Let's start by looking at an example. So here I've just got some arbitrary function sketched. And what I'm interested in is, well, maybe first I'm interested in where is it increasing and where is it decreasing. Where is the function increasing and where is it decreasing? So I can indicate those here. So the red portions are where the function's increasing, the green portions are where it's decreasing. Now, can we make any connection between where it's increasing and decreasing with the derivative or the second derivative? So let's plot a tangent line. So I'm looking at a point. Notice that when I'm on a portion of the curve where it's increasing, the slope of the tangent line is positive. So that's indicated here. F prime of this particular point, negative 1.33, is a positive number. And at all these points where the function is increasing, our derivative is positive. And when we go on to a portion of the curve where it's decreasing, we get that the value of the derivative is negative. And similarly over here where it's increasing, we're back to the derivative being positive. So already we're starting to see this connection that the places where the function is increasing or decreasing are precisely determined by where the derivative is either positive or negative. Positive derivative, increasing function. Negative derivative, function's decreasing. Okay, so that's our first observation. And we're going to formalize this and we'll do a few examples of this, but we're just sort of collecting these ideas right now. Now, what other kinds of shapes do we have for these? So we've talked about increasing and decreasing. What else is there? Well, look back at our original curve. There are some places where it's sort of shaped like an upside down shaped bowl. There's also places where it looks like a right side up bowl. So, this part of the curve over here looks like a right side up bowl, whereas this one looks like an upside down bowl. Those are referred to as concave up or concave down. If it's a bowl opening in the upward direction, or if the curve's opening in the upward direction, we say it's concave up. And similarly, if it's opening in the downward direction, we say it's concave down. Now, how can we get this information about whether it's concave up or concave down from the function or its derivatives? Well, let's look at what happens when we're on a portion of the curve where it's concave down. As I'm sweeping along the curve on a concave down portion, what's happening to my tangent lines? Well, their slopes are decreasing. The tangent slope is getting less and less steep. So the derivative is decreasing. Oh, but if the derivative is decreasing, the derivative is a decreasing function, then its derivative must be negative. Well, that's the second derivative of the function. So, and what do we notice? We notice that the second derivative is negative at the point we're interested in. All these points along this concave down portion, the second derivative is negative. Okay, does that happen on the concave up portion? Well, on a concave up portion, if I'm sweeping along points on the concave up portion, notice that the derivative is increasing in value. So the derivative is increasing. If the derivative is increasing, its derivative, or the second derivative, must be positive. And so we notice that on all these points along this concave up portion, the second derivative is positive. So the second derivative seems to be telling us information about the shape, whether it's sort of opening upwards or opening downwards, the shape of the curve. So we get whether it's increasing or decreasing from the sign of the first derivative, and whether it's opening up or opening down, or concave up or concave down from the sign of the second derivative. That's essentially most of what we're going to talk about in today's lecture. We're going to go through and do a few examples and solidify this. But that's the big idea, is that first derivative, the sign of it tells us intervals of increase, decrease. Second derivative, the sign of it tells us whether it's concave up or concave down. Now, one of the things to notice here is that, let's look at this point right down here. So there's a minimum, a local minimum. Its derivative is 0 there. To the left of that local minimum, the derivative is negative. To the right of the local minimum, the derivative is positive. And that's going to be a way how we can decide if we found a critical point, does it correspond to a local max or local min? What we do is we just peek a little bit to the left of it, see what sign the derivative is, peek a little bit to the right of it, see what sign the derivative is. If it goes from negative to positive, then it must be a minimum. However, in this case, if it went from positive on the left to the derivative being negative on the right, then it must have been a local max. And that's what we're going to call the first derivative test for local extrema. Once I know a critical point, I want to figure out whether there's a max or a min there. I look at the sign of the derivative to the left and to the right and see how it changes sign. And the last thing we're going to look at is what's known as the second derivative test for local extrema. So we could use that first derivative test that we just mentioned. Is it going from positive slope to a negative slope as we move across the critical point? If it is, it's a maximum. But this picture also suggests that maybe we don't even need to look at the slope at either side. If I know the sign of the second derivative at that point, then I could tell whether it's on a concave down portion or a concave up portion. So if I look at this point here, that critical number, and I compute its second derivative, I see that it's negative. So it's a negative value. So it must be on a concave down portion. So it had to have been the maximum. So that should be a local max. So that's how we could use the second derivative to test a critical point for local extrema. Just look at the sign of the second derivative. Is it negative? It's concave down, therefore it must have been a maximum. Or is it positive, in which case the curve is concave up there, in which case it must be a local minimum. And that's known as the second derivative test for local extrema. So basically, with this diagram in our initial discussion, we've essentially tackled everything we're going to look at in this particular lecture. Now let's go ahead and look at the individual details of each of these ideas.